right, so this week we're going to look at our last section for Chapter 8, which is on exponential decay. Okay. If you guys understood exponential growth, or you kind of had an idea of what was going on there, this is pretty much the same thing, except instead of the graph going up very quickly, it's going to go down very quickly. Okay. What's nice about exponential growth, okay, is that it uses the exponential decay, uses the exact same equation as exponential growth. Y equals A times B to the x.
Yeah, you guys have a blank for that on your sheet.
Okay. What's going to end up happening here is that A still has to be greater than 0. Okay, that's exactly the same as it was last week. But B is going to be a little different. Okay? It says y equals ab to the x, and it says a is greater than 0. And notice what it says about b. It says b is bigger than 0, but it's less than 1. This right here, that's the whole thing that's going to make it decay. Now we're going to have fractions for b. We're not going to have numbers bigger than 1. So let me show you guys an example of growth. Okay. Let's type in y equals 2 to the x and look at a picture of that. Okay, so what you're seeing traced in blue, that's an example of growth, because as you go to the right, it goes up very quickly. Okay. Here's an example of decay. What value did I type in for my number that's below the exponent this time? I typed in 1/2. Okay? So I just typed in for the number that's below the exponent, I typed in something between 0 and 1. Everyone agrees 1/2 is between 0 and 1? Okay. Now watch what happens when I hit graph. It's going to come in red. And notice it's a mirror image. You can see it pretty clearly there. The red graph comes down very quickly. Okay? That's an example of decay. It really is a mirror image.
You would say that the graph goes down to the right.
Down to the right.
Yeah.
Yep.
So down to the right for decay, then if it rises up to the right, it's going to be growth.
So as Mr. Roy just said, as you go to the right, from left to right, it's going down. Okay, and notice, what does it look like that red line is getting pretty close to? What axis? Caitlin? Yeah, it's getting pretty close to which axis? The red line's getting pretty close to the vertical axis? I think it's getting close to the vertical axis.
Why?
That's the vertical, right?
Yes.
Yeah, it's not getting close to the vertical. As you head to the right, that red line, to me, it looks like the red line is traced right on top of the x-axis.
I thought you said it was the vertical axis.
So that red line is getting closer and closer to the x-axis. What's our y value when we're getting close to the x-axis? We're getting closer and closer to what number? We're getting closer and closer to 0. Okay? And notice if I look at just look at the column in red. Okay? Watch what happens as x gets bigger and bigger. Okay? We start at 1/2, 1/4, 0.125. Okay? We're getting into numbers that are smaller and smaller and smaller, but they never actually reach 0. So what that means is that as you graph this, here's your x-axis, here's your curve, it's going to get lower and lower and lower and lower and lower, but it's never actually going to touch the x-axis. It never actually hits 0. Okay? And I'll talk a little bit more about that when we get into a word problem. Okay? And explain what that means. right, so let's try an example. Okay, this one they just want us to look at the graph and figure out if we have growth or decay.
Let me tell you, there's some steps on that below there too.
Some steps. Oh yeah, okay, thank you. All right, so looking at that graph, is that growth or is that decay? Look at that picture. Jalen? Decay? How come? So with growth and decay, they both never touch the x-axis. So you want to look at the direction that that kind of curves in as you go to the right. What's happening?
Would it be growth?
Yeah, it's growth because it's heading up,
Up to the right.
right? It's heading up as you go to the right. This would be decay if it headed down.
So guys,
to the right.
don't worry about those lines. We're gonna show you guys in a second what you're gonna write there.
Okay, so the first part of the question, tell if the graph is exponential growth or decay. This is exponential growth. Okay, now the second part of the question says write a rule for the function. Okay, so to do that, we've got some steps.
And the first, guys, that first step, we already did. All right? That, is it exponential growth or decay? So the first thing, when I ask you to do something like this, the first thing you're going to do is figure out whether it's exponential growth or exponential decay. And we already talked about that. If it goes up to the right, it's growth. Down to the right, it's decay. All right, so that's the first step. We already did that. This is based on looking at the graph. What you see there visually, is it growth or decay? So step one, exponential growth or decay. If you know when it's going up to the right, if you know it's growth, and down to the right, you know it's decay, you don't have to write that. All right?
Yes.
Exponential growth or decay.
All right, so now we need to write a formula. Basically something that if I were to type it in on this screen, I would get the exact same picture we have right up above. Okay. Can somebody remind me what the formula is? Yep, y equals a times b to the x. Okay? And does anybody remember when we're looking at a table, how do you get a? Anybody remember how we get a when we're looking at a table? Yep.
The x value is 0.
Okay, I'm going to write that for a second. When x is 0, what did you say?
When x is 0, then close to a.
Close. When x is 0, what else do we have to do? Look at the y. That's the key. When x is 0, look at y. Exactly what we did at a table. When x is 0, look at the y. Okay, look back at that graph for a second. Did anybody see a coordinate there where x is 0? Oh, Ben?
Yeah,
Yep.
it says 10.
Yeah.
So it would be 10.
There you
It's
go.
10.
Y is, a is 10. When x is 0, look at the y, whether it's written as a coordinate or whether it's in a table. It's exactly the same thing we did last week. Does anybody remember what this is called? Where it's crossing right here? This point has a special name.
And think about the axis that it's crossing on.
What do we call it when a line crosses an axis?
Or even in the case of that example, what axis is it crossing? What axis is it going through? Huh? The y, right? So when the line, I don't care if it's exponential, I don't care if it's linear, when the line goes through the y-axis, what do we call it? Anybody remember? Where it crosses the y-axis?
Remember what the b is in the y equals mx plus b slope formula?
Right, y-intercept.
The y-intercept. Okay, it's the b in that slope-intercept formula.
And for that example, the coordinate that it gave you happened to be on the y-intercept. All right? It's not always gonna, and that's not always gonna happen.
All right, so we've got our A value. But now we still need to find one other letter. Okay, we still need to find B. Okay, and the directions right here tell us how to do it. Use the other coordinate. So let me go back up and see what the other coordinate was. 1, 12. What's the x value in that coordinate I just wrote down? 1. What's the y value? 12. And it says use that coordinate. I just labeled the x and the y. And now I'm going to solve for b. So I know a, I know x, and I know y. There's one letter I don't know, b. Okay, gauge, what's y from what I just wrote down? 12. So I'm going to fill that in right there. 12. Okay. Rose, what's a? A is 10. So I'm going to fill that in right there. B, I don't know. That's what I'm going to solve for. I'm solving for B. And x is going to be 1. And I'm going to fill that in right there. All right. So now, a little space. What's b to the first power? Well, what happens when you raise anything to the first power? Does it change it? No. So b to the first power is just b. Okay, so we have 12 times 10 b. And my last step is I need to put this 10 on the other side, and then I'll know b. Okay, how do I get that 10 on the other side? How do we divide it? You sure?
Yes.
Okay, good. Yeah, we're going to divide by 10 on each side because we had 10 times b. Think of what's the opposite of multiplying. Dividing. And that's b. Okay, right there. 12 tenths equals b. We can do something with that. Anybody see what you can do with the fraction 12 tenths? About Davin? Yeah, we can reduce it. And what could you reduce it by?
One number was in the both 12 and 10.
2.
Thank you, Dan.
Yeah.
2?
All right.
How many times does 2 go into 12? Yep. And into 10? 5. All right. So now we've got the two numbers we really need. We've got A, we've got B. Now just fill them into our formula. Fill in A and B. All right, so I've got y equals AB to the x. Final answer, just fill in for A and B. Okay, A is 10 times B is 6/5 to the x. What about this function makes it exponential growth? Even if you didn't give me a picture of this, I could look at what I just circled and say, yep, it's exponential growth. How come?
Because of the exponent?
Not because of the exponent. The exponent's just a letter. I don't know anything just by looking at the exponent, but looking at something else. Yeah, what about this fraction? What did we say? We said something about exponential decay, and I know that this is different. Yep.
It's bigger than 1.
Exactly. If that number that's below the exponent is bigger than 1, it's exponential growth. If I take 6 and divide by 5, I get 1.2. Okay? It's not growing quickly, but it is growing slowly. Okay? Good, so good job.
Go back up for a second.
Yep. All right, so any questions on how we got that equation?
What was number 1?
Step 1? Let's see, step 1 was just to define or write down whether it's growth or decay. So growth, I'll put a picture under each one. Growth looks like that. Decay looks like that. They actually are mirrors. They're like mirror images of each other. All right, so let's take a look at this one and see if we can go through all the steps again. All right, so step 1, is this growth or is this decay? Yep, it's definitely decay. Okay, look at the curve. It's heading down as you head to the right. It's decaying. Okay, any questions on that? So we know it's exponential decay. Let's just write that down. So this is exponential decay. All right, so we answered the first half. Now, the second half says write a rule for the function. Okay, somebody remind me again, what's my formula? We've been using it a lot.
Y equals A times B.
Good. Y equals A times B to the x. And the two letters I need to figure out here are A and B. Let's start with A. Okay. Looking at that graph, anyone think they can tell me what A is? Sabrina? Yep. A, if you're thinking about it as a table, look at the x value when it's 0, and then find the y value. Okay? So when the x value is 0, the y value is 8. That's your A. Or, if you want to think of it as the picture, where does it cross the axis? 8. Same thing. Okay? So that's A. Now, to find B, I need to use something else in that picture. Anybody remember what else I need to use in that picture to find B?
The other coordinate.
Yeah, I got to use the other coordinate. Okay, the other coordinate is 1, 4. Right, Sam, what's the 1? Yep, it's the x. And what's 4? That's my y. So now, look at, I've got 3 out of the 4 letters. I've got A, I've got x, I've got y. The only one I need, B. So fill in all these letters. Fill in 4 for y. Fill in 8 for A. And fill in 1 for x. Okay, and let's solve for b. Okay, we had this last time, b to the first power. That just stays as b. And last step to get b by itself, Justin. How do I get that 8 on the other side?
Divide.
Yep, divide
Eight.
by 8 and by 8. So anybody think they can tell me what b is? If I reduce 4 over 8?
1/2.
Yep, 1/2. All right, so now we've got the 2 important values we need. We have A and we have B. What's my last step that I need to do with the A and the B? Yeah, we have to actually plug it in and now write the rule. So it's y equals A times B to the x. And that's your formula. Now, looking at this formula, who can tell me why is this decay? if you didn't even have a picture, you should be able to look at that and say, yep, that's going to be decay. What number there tells you? Yeah?
Greater than 0 and less than 1.
What is? B. Yep. The number that's below the exponent is between 0 and 1. Anytime that happens, it's going to be decay. Perfect. Okay. So, any question on the formula? Yes?
Why do you have to say like the number between the exponent, like underneath the exponent? Like would there ever be a case where it wasn't like B, or could you just see B?
It's always going to be B.
Okay.
What that tells you if it's decay or growth. Yep. Just look at that number right there. Yep. This number in front, does anybody remember what the number in front does? 2 words. We talked about that last week. What does the number in front cause to happen? It was something by a factor of, and in this case it would be a factor of 8. Anybody remember that? Began with a V.
Vertical stretch.
Yeah, vertical stretch. Okay, the number in front, that's a vertical stretch by a factor of 8. Right? But we're not worrying about that right now. All right, so what we can do is we can use exponential decay in word problems. As long as something is decreasing by the same percent over time. So we did a problem where like the value of a car gained 4% every year. Well, with exponential decay, it's like the value of the car would lose 4% every year. Right? That's an example of a decay problem. And here is your formula. Okay. Do you guys have a spot on your reference sheet to write that down? Yep, so make sure you copy that down. And there's only one difference between this formula and the formula for exponential growth. There's only one thing that's different. Does anybody think they see the difference between this one and exponential growth? Justin?
In the middle of minus R.
That's it. That's the only thing that's different. It's minus R instead of plus R. For decay, it's going to be 1 minus. For growth, it's 1 plus. A is still the initial amount. Okay, that's how much something might have been worth or a population. And T is our time period. And usually we measure the time period in years. Okay, one example where you see exponential decay sometimes is with like nuclear reactors. Anybody remember that nuclear reactor in Japan? It got hit by the tsunami. Yeah, it melted down and it's giving off radiation for a long time. Well, just to kind of simplify it, let's say that when it started out, it was giving off, I'm just going to make up a number, 500 units of pollution. Okay, that's how much pollution it was giving off. And let's say that every month it goes down 5%. Okay, so after 1 month, I'm just going to multiply by 0.95 because that's 95%. So after 1 month, it's no longer 500 units. Now it went down to 475 units. So it's less pollution. I'm going to do it again. After another month, it goes down to 451 units. After 3 months, 4 months, 5 months, 6 months, 7 months, 8. What's happening to the number? It's decreasing, but watch what happens if I just start hitting enter very fast. Okay, it's still decreasing. It's decreasing, it's decreasing. Now I've hit it probably a couple hundred times. What number is it getting close to? It's getting close to 0, but watch what happens if I keep clicking. 0.5, 0.4, 0.3. It's never going to hit 0. It's going to get closer and closer and closer, but I can keep clicking it all day. It's never going to hit zero.
Why? Because there's so many numbers.
Wait, do we try to hit 0?
No, you never will.
Never?
No. So basically, what that means is that the amount of pollution there, it's going to get lower and lower and lower and lower, but there's always going to be a little bit left. Okay, that's the problem with nuclear energy. The pollution that you create from nuclear energy. Okay, it's not clean, right? There's always a little bit of pollution left. I mean, it's not the worst, but there's always a little bit of nuclear. They call this nuclear radioactivity. Okay, anytime you have something that's radioactive, there's always a little bit of pollution left. You can never get rid of it completely. Eventually, it gets small enough that it's not as harmful. Okay, but it never hits zero. All right. So that's the problem with some kind of nuclear radiation. There's always a little bit left. Okay.
I had a question about like, the equation.
Yep. Question about the equation.
Yeah, on the board, the arrow is pointing to the R, but on our paper it's pointing to the line. Which is supposed to point to?
So the initial amount should point to A. The decay rate should point to R. And the time period should point to T, because that's time. Okay. Any other questions on the formula? All right. So let's take a look at an example. Okay. This one it's not about nuclear energy. It says it's about a forest, and it says the amount of forest decreased in the western U.S. by 0.5% every year from 1963 to 2002. Okay, so because it's decreasing the same percent, it's not a lot. It's only 0.5%. But think about if you decrease something by 0.5% for many, 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 many years, then it starts to add up. Okay, so the amount of forest is going to decrease by 0.5% every year from 1963 to 2002. And in 1963, we started out with 41 million acres of forests. Okay. Do you guys already have that on your sheet? Okay. So, first thing let's figure out is let's write a formula to represent this situation. Okay, and I'm going to just call this part A. All right, so write a formula to model the situation. Now, if this was on the test and they said, they didn't tell you whether this was growth or decay, does anybody see a word somewhere in that problem that tells you this is about something going down over time? It's not going up over time. Everybody see? Yep.
Decrease.
Good. Decreased. Okay. This is about something going down. Okay. We'd rather it be going up, right? We'd rather have more acres of forest rather than rest, but it's going down. Okay. So it's going down over time. Right. So few things we need to figure out to write a formula. First thing I need an initial amount. Okay, reading that word problem, do I have an initial amount of forest that I'm starting off with? What is my initial amount of forest? Yeah, 41 million acres. Okay, so my initial amount of forest. Okay, I'm just going to write initial amount is 41. And again, remember that represents million. Okay, I'm not going to write out 41, 000, 000. I'm just going to write the number 41. That's 41 million acres. All right, so I got that. How about a decay rate? Okay, do I have a rate of decay, or how much of the forest I'm losing every year? Yep, we're losing 0.5% every year. Now to change that to a decimal, which, again, the directions say we've got to make sure we do, I move this decimal 2 places which way? Yep, to the left. So what's that going to become if I move it 2 places to the left? No, not 0.05. Yeah, it's 2.005. So again, you might think, well, boy, that's such a small number, right? You're not losing that much forest. But if you do it 20, 30, 40, 100, 200 years, it starts to add up. All right, so that's my decay rate. And in this case, we don't have a time. Okay, there was no time. It didn't say find how much of the forest would be left after 30 years. That's what we'll do next. Right? So now we're just going to fill in those numbers into our formula. All right, so y equals, right, Kevin, what was my initial amount of forest? I'm going to fill that in for A. Yep, so that represents 41. Remember, that's not 41 acres. That's 41 million acres. Okay? Times 1 minus, Victor, what's my decay rate? Right. Logie, can you help Victor out?
0.005.
0.005. Okay, so fill that in for R. And T, I don't know. Okay, the only thing I'm going to do on my calculator is I'm going to do 1 minus 0.005 just to see what it comes out to. Okay, you can always do what's inside the parentheses. 1 minus 0.005 gives me 0.995. Okay, so there's part A. That is your equation for how much forest will be left if it keeps decreasing at 0.5% per year. That assumes it never changes. Okay? If it changed, that's more complicated. All right, so part B. Let's find out how much forest would be left in 2002. Okay, so we started with 41 million acres. Let's see how much is left in 2002. So how much forest is left in 2002? So I have to figure out how many years have gone by from 1960, what was it? 1963 to 2002. Yeah, just subtract the two. Let's take 2002 minus 1963. That's 39 years. So what letter is that going to be plugged in for in my formula? T. So I'm just going to put, in this case, T equals 39. And how did we do it? We did 2002 minus, what was it, 1963, thank you. All right, let's fill it in and see what we get. So y is going to be how much forest is left. Okay, do you think we're going to lose a lot of forest? What do you think? A little bit? Yeah, let's see what happens. So we got 0.995 to the 39th power. All right, so I'm going to use this calculator just because I think it's a little bigger. You can hopefully see the screen better. I've got 41 times 0.995 raised to the 39th power. Okay, so we started out with 41 million acres. How much is left after 39 years? But Zach, can you tell me how much would be left? Just reading off what's on the calculator. Can't see it? Okay, hold on. 33, careful, not 33,000. Million. Okay, so we'd have about 33, I'm just going to say 33.7 million acres. So how could we figure out how much forest we lost? What if they said, how much did we lose over the last 39 years? What would you do? Oh, Gage? So we've got 33.7 million acres now. And they want us to know how much forest did we lose?
Just times that are divided by how many years?
No, not how many years. Anybody help them out? How would we figure out how much of the forest we lost? Just how many acres? Oh, Kevin? Like if I said to you, okay, how many, let's say fires burned down this forest, right? I said, this is how much we have left. And somebody said, well, how much of the forest did we lose? How many acres got burned down? What else do you have to know? This is how much is left now, but you also have to know how much you started with. Okay, I'll tell you we started with 41 million acres. So if we started with 41 million and this is all that's left, yeah, what do you do? And how'd you get that? Yep.
You subtract it.
Yeah. So if they said to you, find out how much of the forest burned down, just take your 41 million acres and subtract how much is actually still left, and we could see we lost 7.3 million acres. And then maybe if we knew how many trees on average we had per acre of forest, then we could actually figure out how many trees actually burned down. Not exactly, but we could maybe estimate how many millions or billions of trees we lost. All right. Okay, so any questions on coming up with a formula or then using it to find out how much forest was left? All right, so that's all we're going to take a look at today. So the homework will be a worksheet on 8.6, part 2. Remember, we'll go back tomorrow and we'll take a look at part 1. And then you guys get a little break with the MCAS, and then a review day on Thursday with an MCAS question.